Hey everyone, this is Mr. Logeman here. And again, if you haven't met me or you don't know who I am, I'm the student teacher working with Mr. Geiselhart, and so I'll be helping out a lot over the next several weeks. But today we're going to be studying the surface area and volume of cylinders. Now, there's two really important things you have going for you as we approach the problems this week. One, I think you all have a good idea of what a cylinder is. While last week when we were discussing prisms, I think we had to work a little harder to get a sense of what those different shapes are. When I say cylinder, I'm pretty sure a lot of you have a good idea in your head of what that is. You've seen them, you've heard of them, and images come into your mind when I say that. So that's very helpful. We'll still talk about the structure of it, but you have some good background knowledge. Second, last week we studied the surface area and volume of prisms. And while they are different in some ways, there's a lot of similarities, and I think you'll find the problems this week going a little bit smoother than last week if you struggled with those problems. So for those of you that maybe have forgotten about what a cylinder is or you need a refresher, I have a few classic cylinder examples on the screen here. In the top left, we have Pringles. I love Pringles, a great snack. Then we have a pop can, and yes, there's a little slant here, so it's not a perfect cylinder, but it has the same idea or the same structure as most cylinders. Down here, we have some firewood, a very nice log that's in the shape of a cylinder. Some canned foods. Most cans are going to be in the shape of a cylinder. Down here, the Leaning Tower of Pisa. I don't know if you know about that or where it's from, but it's a very famous tower, and it's in a pretty cylinder-like shape. It's not perfect, but it's close to it, but it's actually tilting. And as you see, or as you'll see, we're going to have some problems where we do have some cylinders that are tilted or not exactly straight up and down, and we'll see how that changes our problems going forward. And then most importantly, I think in this weird COVID-19 era up here, we have a very nice roll of toilet paper, and I really hope for your sake that the radius of that cylinder is a little bit bigger than the inner cardboard circle. If not, you're going to be in some trouble. And then down here, I have more of a mathematical diagram of a cylinder. It is a diagram that has the radius and the height shown on that figure. And again, with prisms and cylinders, when we say height, we're talking about the distance between the bases. So in general, with these problems, with prisms and cylinders, we've said that there's two bases that are congruent and parallel or opposite, and then there are sides that connect those bases called the lateral surfaces. And the height, or the distance between the bases, is part of that lateral surface. And while this is only true for right cylinders, and I'll get to in a second what the other kind of cylinders are, for a right cylinder, the radius and the height are the only two measurements that define that shape. So if I gave you the radius and the height of a cylinder, you could recreate it. Now, if we don't have a right cylinder, that means it can tilt a little bit, so you need to know the angle. But for your normal cylinder, the radius and the height are the two most important and really the two only measurements for that shape. So let's go forward here one slide. It'll help you a lot if you go to your Canvas and you select the assignment that's called 9 SA and V of cylinders, which stands for surface area and volume of cylinders. And this lesson that I'm making right now is going to give some more explanation than just the problems, but it will go through the problems on that assignment exactly. So if you want some points for less work, that's a great way to do it, is to have that video going alongside, or sorry, your assignment going alongside this video. So go there right now. You can pause and go there, and that will help. So I want to briefly mention what a right cylinder is, because I talk about that a little bit in the first slide. And a right cylinder is a specific kind of cylinder where the circles or the bases are directly above and below each other, or those congruent bases are parallel to each other. Meaning if you took a line from the center of the top circle to the center of the bottom circle, that's going to form an exact right angle with both of those circles, which you can see here with this right angle symbol. And that would be the same on the edge, either edge, but the center is a great way to look at it. And so that's the first problem we're going to talk about for this assignment. So first, let's talk about what the structure of a cylinder really is and how that affects our study of the surface area. So I know last week you talked about surface area being the area of the two bases and then also the surface area of all the lateral surfaces. And it's going to be the same here, but it's maybe not as apparent or obvious what that lateral surface is for a cylinder. So I'd actually encourage you to take a pause in this video if you want and look at a few cylinders and try to imagine what that lateral surface actually is. But I will explain it here in a second with a handy dandy toilet paper roll. Like I mentioned in the first slide, very important, and this is a bad situation where it's empty, but it's okay because it's actually going to be a great lesson. So here we don't have the bases defined or filled in, but the structure of the cylinder is the same. So let's look at the surface that makes up the distance between the two bases, or the lateral surfaces. And how might we find the area of that? Well, you'll notice if we were to unroll it or split it out, like the nets we saw last week where we sort of unraveled that prism, same here. If we were to cut this surface open and unravel it, you'll notice we actually have a rectangle. And here, one side of the rectangle, right here, is the height of the cylinder, that distance between the bases. But what is the top of the rectangle? Well, if you roll it up, you'll notice that it's just the circumference of the toilet paper roll. So the lateral surface is really a rectangle with the height for one side and the circumference for the other. So let's get started with the first problem here, which is going to be the surface area of the right cylinder. So just as we did with prisms last week, we want to find the area of the two bases first. And with cylinders, similar to triangular prisms, we always know what the bases are. Whereas rectangular prisms, you had some decisions to make. Here, the circles on the edge or on the sides or on the top and bottom will always be your bases. So that's what we can do right away, is find the area of that. So I think you all remember what the area of a circle is. If you don't, it's pi r squared. But to get the area of both bases, we're going to need to double that. So we're going to have A equals 2. And actually, I'm going to write 2b, because if you remember last week with prisms, that big B stands for the area of the base. So 2b is a good way to write that. So 2b equals 2 times pi times r squared. And now with the annotation or the writing tools here, I have to write squared with this little caret symbol, but that just means r squared, okay? And now all we need to do is plug in the numbers. But be very careful, in this diagram, I have not given you the radius. If you notice, this 14 right here is labeling this line, which goes all the way across the circle through the center, and that's the diameter. And if you remember, a diameter is just twice as long as the radius. So we want 7 for our radius. So we're going to get 2 pi times 7 squared. 7 squared is 49, times 2 is 98. So we're going to get 98 pi, which comes out to a grand total of 307.88. So that's the area of our two bases. So now we want to find the lateral surface area, which again is the surface that connects the two bases. And here it is one surface, it's that rectangle, which is the circumference times the height of the prism. So we know the height of the prism is 19. So now all we need to do is find the circumference. And remember also with circumference, the formula you may know is 2 pi r, where the circumference equals 2 times pi times the radius. But also 2 times radius is just diameter. So in this case, where you're given the diameter, it's probably more effective to just think of it as pi times the diameter. So our circumference is pi times diameter, and then we need the height. So I'm going to write LSA for lateral surface area equals pi times d, pi times diameter, which means circumference. So I'll put that in parentheses just so you know that that's the circumference portion, times your height. And filling in our numbers, we're going to get pi times 7. Oh, excuse me, pi times 14, because we do use that diameter here, times 19. And that'll equal 266 pi, which is a grand total of 835.66. So now we've found all we need for the total surface area, because the surface area just asks to find the area of all the surfaces of a three-dimensional shape. And we only have 3 here, and we've found the 2 bases and the lateral surface. So all we need to do is just add those 2 together. So 307.88 plus 835.66 is 1,143.54. And that's all you need to do to find the total surface area of a right cylinder. So let's go ahead now, and we are going to look at the volume of a cylinder. And this is one of those cases where I think it is really a pretty simple transition from prisms to cylinders. because with prisms, you said that the volume equals big B, which is area of the base, times your height. And it's exactly the same case here. Area of a circle is pi r squared. So I'll write that here one more time. So we have it pi r squared times height. And in this case, we'll get pi times r squared is 7 squared, remember, times our height is 19. And that will equal, let me see my notes here, that's going to equal 931 pi. And if you plug that in your calculator, you're going to get a total of 2,924.82. And that's all it takes for this first problem. Not too hard. And really, I think these problems are very similar to prisms. Think again for the lateral surface area and the area of the base is. For the prisms, one of the tricks we had was the perimeter of the base times the height for the lateral surface area. And just remember that perimeter is the outside of a shape, and circumference is really the perimeter of a circle. We just have a fancier name for it because it's a very specific component of a circle that we can study in a lot of different ways. So really that trick applies here the same way, where the lateral surface area was the circumference times the height. So problem number 2 is a half cylinder. And this is going to change the surface area and the volume in different ways. It's actually going to cause more of a difference for the surface area than the volume. I bet if you think for a second how it will affect volume, you probably can figure that out by just thinking of the structure of the shape. But let's talk about the surface area. So again, we want to look at the area of all the surfaces on a three-dimensional shape. And for a regular right cylinder, we had 3 surfaces. But how many surfaces do we have for this shape? Well, we actually have one additional surface. We have our 2 bases. It's those semicircles on either end of the shape. Then we have half of that curved surface, or half of what would have been the curved surface for a full cylinder. But then because we sliced this straight through the diameters, we have this rectangle on bottom. Now this problem does pose a great situation where we have to consider what the bases are, because it's another reminder that base does not equal the bottom of the shape. And that's very true here. The bottom of the shape is this rectangle, but there's no congruent shape on the opposite side that would make it the base. So it's just the bottom of the shape, but it's not the bases. The bases are the semicircles, because those are your congruent parallel shapes. So let's try to find the area of the 2 bases together. So again, our area is going to equal 2 times big B, which is area of the base. And so what is the area of a semicircle? Well, it's half of a circle. And so half of a circle would be pi times r squared times 0.5, or divided by 2, because it's just half of that circle. But you'll notice now we times by 2 to get both bases, and then we're dividing by 2. So we can really just cancel those out, and we can look at this as the area of both bases together is just pi r squared. Because if you have 2 semicircles, that forms one complete circle, or full circle on its own. So we're going to get pi times 20 squared, which equals 400 pi. Mix them out a little bit. And 400 pi is going to equal 1,256.64. So not too hard there. The lateral surface area is where it gets a little funkier, because we have 2 surfaces now instead of 1. So first, let's figure out this curved surface. So again, we want to think about how we found that curved surface in the original problem, and that was finding the circumference of the circle times the height. So that's one way we can do it, taking that and dividing by 2. So I'll do that first. I'm going to call CSA our curved surface area. So that's one part of the lateral surface area. And so for that, we're going to do circumference again. And here I've given you the radius. So we probably want to use the 2 pi r. So 2 pi r times our height. And then we're going to divide by 2, because we've sliced that curved surface in half. And so that would equal 2 times pi times 20 times 27. And then we'll divide by 2. And that would give us a total of 540 pi, which equals 1,694.46. But then we also need to find the bottom, and that's that rectangle. So I'm going to write bottom equals, and rectangles again are just length times width. That's how you find the area of a rectangle. And here, the length is the diameter of the circle, and the width is the height. So that's pretty straightforward. We're going to just do d times h. And that's going to equal 40 times 27, which equals 1,080. So then for the total lateral surface area, we need to add those two surfaces together, the curved portion and the bottom portion. And together, that'll get us 2,776.46. That's the lateral surface area. Now here, I want to say you do have one more option related to that perimeter times the height. One thing you could do is you could take the perimeter of this base, so you take half the circumference plus the diameter and then times by the height, because that'll do the same thing as before. That'll get one rectangle, which is half circumference times the height for the curved surface, and the other rectangle is the diameter times the height. Either way that works better for you is fine. I've split it into two parts because that makes more sense for me, but if you want to find what you would call the perimeter of this semicircle and times by the height, that is totally fine as well. But remember, we're not done with the surface area yet, because we need to add the area of the bases plus the total, or the lateral surface area. And that'll get us a total of 4,033.10. I want to again remind you of the formula. Here for TSA, what we can do is pi r squared gets the area of both the bases. The curved surface can be found using pi rh, and that bottom rectangle is the diameter times the height. Going forward for the volume. Here, again, there are two ways to think about it, but they do the same thing. So the two ways to think about it. A, we can again find the area of the base and times by the height. So we would take half the area of a circle and then times by the height. Or you can think about finding the volume of the full cylinder, that has these measurements, and then dividing by 2. And I'll show you those are just the same. So volume equals area of base times the height. And the area of the base would be pi r squared divided by 2 times our height. What we could have also done is gone pi r squared for the area of the full circle times our height, and then divided by 2. So this divided by 2 can either be in the actual area of the base portion, or at the end if you were to consider finding the volume of the whole cylinder. Again, either way is fine, because division and multiplication are commutative. So we can do that here, this division here, or at the very end. Doesn't matter in this case. So I'm going to leave that as it is, and that will give us pi times r squared, and r in this case is 20, times then I divided by 2, times our height, which is 27. And that would give us a total of 5,400 times pi. And if we multiply that in our calculators, it's a pretty big number. We get 16,964.60. And your numbers may get very large. That's okay. As long as you're doing the process correctly, you should be just fine. All right, for the final problem, it's going to talk about this type of cylinder called an oblique cylinder. And that's what I referenced earlier, where we have that slanted cylinder, so there's an angle involved. Because a right cylinder goes straight up and down, right? We have the circle on top, circle on bottom, straight above and below each other. Here, it's offset, where there's a circle on bottom and a circle on top, but they're not directly above and below each other. They've shifted to the side a little bit. So there would actually be an angle sharing how far that is offset. So if you wanted to recreate that cylinder, you would need to know the radius, the height, and the angle that caused it to offset. But how is this going to affect our volume and surface area? Well, we're actually going to look at the volume, because I'm going to tell you the volume, it is a lot easier than you may expect. But the surface area is very complicated, and I'll explain that in a second at the very end of the video if you want a challenge. But how would the volume change for an oblique cylinder or a slanted cylinder? Well, let's look at these poker chips as an example of how this works. So this here would be a right cylinder, because these poker chips have a chip on top as the base and the bottom is a base, and directly above and below each other at a right angle. Here, they've offset those poker chips, but how did that cause the volume to change? Well, the volume here, we can think of the material in the poker chips. And shifting them to the side does nothing to change the material or the amount of material in those poker chips. Now, yes, there is this little step that causes a little discrepancy. But let's imagine these poker chips were thinner and thinner and thinner. Eventually, if we shifted it to the side, that little step would be smaller and smaller and smaller until eventually it would go to zero. And so actually the volume does not change at all, even if we shift, which is pretty interesting. So we can solve it in a very straightforward manner in this problem. This is the final problem from that assignment. So again, our volume equals the area of the base times the height. And the area of the base is again pi times r squared times our height. So here we're going to get pi times r squared, which is 7 squared, times, and what is the height here? That's a really important consideration because we want the same height that would have been for the right cylinder. So it's actually the up and down or vertical distance between the bases. You'll notice this arrow goes vertically from the bottom base to the top base instead of along the slanted line. If you had this slanted line, you would need to do a little more math to find this vertical distance. So we're going to focus on this vertical distance, which we're going to call the height. So that's going to be times 12, and that will equal 588 pi for a grand total of 1,847.26. And if you've watched this video all the way, thank you for tuning in. But I've given you basically a free point because the second question is what would the volume be of a right cylinder with the same radius and the height? And like we just mentioned, it's exactly the same. So it's 1,847.26. Now, as I mentioned before, the surface area, it's a lot more complicated. So we're not going to worry about this for this unit, but I challenge you if you want to try to figure it out, try to think of it on your own and feel free to email me and we could talk about it because it is possible, just a little more complicated. But that's all the information you need for the surface area and the volume of cylinders for this assignment. So hopefully this helped, and good luck on the assignment this week.